Good morning, Alexei.
Good morning, Sekar.
Hi, good morning, Alexei.
Good morning, Rashmi.
Hello, Alexei.
Good morning, Miguel. Bonjour.
Yeah, Miguel came earlier today, so that yesterday he was a little bit late, so he was extra cautious.
Yeah, I want to repeat the same mistake.
I think there will be a lot of interest as far as the ionization radiation is concerned, the gamma radiation. So we expect questions coming in. We already have, I think, around 24 participants. Attendees 17 around who have already joined us. Maybe we'll give a couple of minutes more before we start. I hope that's okay with everyone.
Yes, no problem.
So how's the weather in France? I think no rainfall now. It's
been a terrible summer. We haven't seen any sunlight for months. Oh, maybe Miguel in the south is better, but here in the north of France, it's just a nightmare. Just spring, gray weather.
I was in Spain for holidays, so.
So you had the sun.
The summer. Yes. My colleagues told me that there's a lot of rain.
A lot of rain, yeah.
Last weeks.
Yeah.
I think it's like global warming. Everyone's got impacted. First was the pandemic, and now I think it's the weather change across the globe. Yeah. You hear US, then you have a lot of companies going into the force majeure scenario. Then Europe also, a lot of rainfall. Yeah. We hadn't expected, this wasn't the season for rainfall. And even in India, we had a couple of cyclones, which hit the coast over here, a lot of delays.
Yeah. And a lot of fire in forest also. In south of Europe, it was dramatic. In Greece, south of France, I don't know in Spain, but in some countries, they have a lot of forest.
But I heard that was in California, in the US, because it was quite a lot in the news that there are forest fires in California. I wasn't aware it happened in Europe also. I thought Europe was comparatively colder. So climate would be...
No. In countries like Greece, it was a disaster.
Yeah. Very close to Athens.
Yeah.
We don't make the news in India.
No.
Because you've been to India anytime, or like your first interaction with Indian audience?
Not yet.
Okay. So I have one scenario proves we can have plan over here with us in India.
Nice.
Maybe they will have soon to buy a facility in India if it works fine.
Should look at one because we are getting a lot of queries. I don't know, but it's like India, like China is very cost competitive. So that's something we've got to look into and see how we manage that.
And it's a easy business case. We are bringing the material, we are bringing the customers. We just need to this facility. So easy, isn't it, Mr. Sekar?
Yeah, and I think there are a lot of big packaging companies in India, and they are like global companies.
Yeah.
Hi, Gils, how are you?
Hello.
I think he's still connecting. I'll just share my...
Yeah, I think we can, what time we can start? People are still joining.
Yeah, I think I'm just giving a basic introduction about what we've already done. So I can start with that. Around 5 minutes. Anyone who's got a little bit late, but definitely adding on more attendees. It's like a topic of huge interest. Almost all the people. Okay, I'll start. Good morning, good afternoon, and good evening to the distinguished panelists, participants, ladies and gentlemen who have logged in from different parts of the globe. I can see people have logged in from different locations across India and also from different locations as far as Middle East or Southeast Asia is concerned. Many people have registered, so I expect soon they also will be joining in. So in this virtual conference, I recognize a few familiar names and participants from the esteemed organizations. So it's heartening to see such a positive response to this webinar, which has basically been a knowledge sharing platform for us. I hope now you can see my screen and I'm audible to all of you. So it is my pleasure to welcome the eminent speakers, participants to the plastics flame retardant system. We will be discussing on Crosslink polymer flame retardant systems today. This webinar is brought to you jointly by Formulated Polymers Limited, Asia, and Eurostar Engineering Plastics Now, Ascent Performance Materials, France. So additionally, we have a special guest with us, Miguel, who will be discussing on the radiation, since we are talking about cross-linking. Since there is a lot of interest which has been generated in the present topic, we had like roughly 500 visitors which had come to our site, and we had more than 100 people who had registered on for this session. So I'll quickly go give a few introductions and start with the presentation. This webinar series 9 is a little bit longer, around 55 minutes of presentation and 10 minutes of question answer. I'm Rashmi Bhardwaj, Vice President Development in Formulated Polymers Limited. I have basically a doctorate in polymer technology, MBA in international business. Would request the participants to post your questions in the QA box and not in the chat box. It'll be much more convenient to have the questions there. This webinar, like we said, it's a knowledge sharing platform for experienced professionals or professionals who are working hands-on in these specific areas. Just to do a quick recap, we have already done all these 6 series where we talked about introduction, the FR mechanism, various testing methods, the standards, the processing of FR compounds. We also had a discussion in terms of the design perspective, like what are the care or what are the features have to be taken into consideration when we are designing any component for flame retardant compounds. And then the environmental impact. It's very important that we take care and ensure REACH and ROHS compliances. Possibly India is not as Europe or as US for the stringency. But I think that part is going to change very soon. And since there is a huge amount of awareness which has been created, there will be definitely changes. And we see them coming. We see the coordination from various teams, systems. This session right now is Crosslink polymer FR systems, which we are discussing now. And then next series will be on the applications, subsequently certain secondary operations, where we'll be discussing with the various team members on what are the cares, precautions, and what is the process for ensuring that we have good laser marking, no color change, etc. And finally, we will be having the last session where we'll be covering up the future trends in the FR system. Just to quickly go through this, although all of these sessions, and this is basically I'm covering for the people who are attending it for the first time, because we have certain participants who joined in fresh. Even like Miguel has joined for the first time on this session. So I'll quickly share with him what all we've been doing right now and how he has come into the picture. So it's very important. We started off with the history in terms of what exactly is and why do fire accidents happen, and why do we come to reaching the stage where flame retardant plastics are being used for certain applications. So we talked about the history, the reasons, the ISO designations. This is available on the YouTube link. So anyone who's missed out, they can quickly go to the YouTube link and see this session. The second was on the flame retardant mechanism, where we discussed various physical and chemical reactions, the endothermic, the radical quenching, the thermal shielding, basically different materials. There was a different system for the flame retardancy and the trend towards more environmental compatible flame retardant systems. So it was critical as we moved away from the halogenated systems, we go for the red phosphorus free and then move forward to the organic phosphorus or some of the other compounds which are now being used. Testing we covered so that we ensured that we are aware regarding what are the critical parameters which have to be tested and how they're tested. Most critical being the UL94 and mobile test, where we had a full one-day session on this. And then we covered on part 2 the limiting oxygen index, smoke density, CTI, the hot wire ignition, the high current arc ignition testing, arc resistance. As well, during this session, we covered up the UL746B, the long-term property evaluations, which are critical for the flame retardant components. These sessions both were done by Alexi and Krishnamurthy, very good sessions. We got a good response, especially from the technical teams who were attending it. Then we had one where we discussed upon standards. And since there is a very low level of awareness, how do you read the UL, how do you read the BDE cards, etc. So Pankaj Chaudhary, the country head from BDE, had joined and presented for the session, along with Prasad Shankarappa, the UL principal engineer from Underwriters Laboratory. We had the next session where we talked about processing FR compounds. What are the care and guidelines which have to be taken into consideration when we are processing? So how is it that our customers evaluate? How is it that the OEMs assess? And then what is it important when we do the processing of the FR compounds? So Satish Kumar, the principal architect, materials and radiology, Schneider Electric Asia, presented along with Alexi, head of technology, Eurostar Engineering Plastics. So we had, after processing, a session where we talked about design perspective, why it is important to have a particular design, and how with this new technologies which are coming in, how we can modify, optimize the design, look at certain aspects like miniaturization. How do we reduce weights as far as automobile or various transport systems are concerned? So we had a session where Pradeep Chaudhary from Design Plus presented, along with Prashant Viragi, Senior DGM Plastics, L&T Division of Schneider Electric. So, and then the last session, we talked about regulations, a lot about regulations in terms of what is REACH, what is ROHS, why is it important, what are the factors which have to be taken into consideration, especially when we look at the export market and even in the domestic market, how these regulations are becoming more and more important. So here we had Amit Bahadur Singh, the product head for TUV, presenting along with Alexi. And now we come to the present series. So here, series 9, which is about Crosslink Polymer FR systems. So for this particular series, we have 3 presenters. And I think cross-linking is new technology, new innovation. And we look at this in terms of our materials, the materials which are being used by Formulated Polymers Limited, Ascent Performance Materials, and radiation support, whatever we can, IONISOS. I would like to introduce the three presenters now. The first presenter we have is Mr. V. Shekhar. He's a polymer engineering graduate with Masters in Business Administration, has around 36 plus years of experience in formulation, compounding, application development for technical parts. After a brief work experience, he co-founded the Formulated Polymers Limited along with Mr. Mohan. And I think the rest is history. So the way the organization has grown, it's something to look forward as a benchmark. The way they have grown from a small organization to one of the key engineering plastic manufacturers in the country. He's the immediate past chairman of the Governing Council of Indian Plastics Institute, the IPI professional body, which has more than 3,000 members. He is also Governing Council member of Plus India Foundation, a past president of the Tamil Nadu Plastics Manufacturers Association, past Governing Council member of CIPET, that's the board which does the entire testing all over India. And has research programs also now. He will be discussing on the Crosslink polymer introduction, the methods, requirements, and applications. Then we have a presentation from Alexei Chopin, who is the technology head with Eurostar and now presently with Ascent Performance Materials. Alexei earned a master's engineering degree in plastics engineering from ITech Leon, and he has over 25 plus years experience in formulation, compounding, application development, as well as custom compounds. He has a very versatile and wide experience in the electrical and electronic segment. Polymides, he has a number of patents, co-applicant of many patents in FR engineering plastics, and a subject specialist as far as low voltage and medium voltage applications are concerned. He will be discussing on STARFLAM grades, the patent, the UL cards which are available, and the applications of Crosslink flame retardant products. Third speaker for today's session is Miguel Morales. He has a bachelor's degree in physics and MBA, has over 20 plus years experience in the irradiation business, working as a general manager in IONISOS, the Spanish subsidiary of the group, and moving to the new sales and marketing director. IONISOS is one of the leading European companies in the field of industrial irradiation, offers its services to plastic medical devices and industrial institutes as well as organizations across Europe. They have multiple locations, and I think that's where Miguel will be sharing more information regarding that. He will be discussing on the principles and potential of radiation, processing of polymers, and irradiation facilities which are available with IONISOS. I think over the session now to Mr. Shekhar to start with the presentation.
Thank you, Rashmi. And maybe I can present my paper.
Should I stop share?
Yeah.
Okay, I'm stopping share.
Is it visible?
Yes, it's visible, but I think this is the last slide. Oh, you're starting. Okay. Yeah, now this is it.
Yeah. Thank you, Rashmi, for the introduction and summing up of all the webinars so far we have done on this series of flame retardants. Okay, this series is about cross-linked flame retardant systems. Okay, we will be concentrating more on polyamide because the product which we are all very familiar with, both Ascent and Real. And we all know what is cross-linking. I think we are all very familiar with the two compound system that take a hardener and a resin and mix it and then becomes cross-linked. So two long molecules, polymer molecules, if some reaction happens between the chain, then they become cross-linked. And there are various ways this chemical reaction can happen, maybe by applying heat, maybe applying pressure, and maybe in some cases we can even change the pH. That is, we can make it either acidic or alkaline to start a reaction. And of course, radiation is also a recent trend by which you can do a cross-linking. And radiation, there are various techniques are there. Anyway, we have specialists today to talk about it. And I don't want to spend on that. Maybe E-beam, gamma radiation, UV light, etc. can also create the cross-linking. And we all know that 100 years ago, or maybe 80, 90 years ago, plastic was started with thermosets. I think even recently, when I was young, years ago, I have seen our bakelite phones, okay, the black colored phones. I don't know whether this generation would have seen that. And thermoset is considered as a darling material for designers of electrical industry because it's quite rigid, it doesn't melt, and it is it is really very good material to handle it, especially for higher the voltage like medium voltage. But unfortunately, thermosets are very slow in production, and the processing cost is very high. And with the miniaturization that is driving the industry today, I think you have to make it parts smaller and smaller and smaller, but there are a lot of limitation in thermoset to reduce the thicknesses or part sizes. So naturally, thermoplastic has to perform those duties. Of course, we know thermoplastic, they are very suitable for thin walled applications, and you can recycle the scrap any number of times till you finally decide. A lot of design flexibility like snap fit, hinged fit, all that is possible in thermoplastic. Of course, they are very fast production. I think today the production cycles are getting reduced, and maybe today it's in the order of something like 10 seconds. Also, we are able to see a complete injection molding cycle. So the processing cost is much lower. So thermoplastic is getting into most of the application. But unfortunately, if there is a peak in temperature, or if there is a soldering with an iron non-lead, lead-free soldering, the temperature goes up, then the thermoplastic softens and causes the problem. So there was a thought, why don't we make a thermoplastic also behave like a thermoset? Okay, this is how this cross-linked thermoplastic started. So it is like processing like thermoplastic. It can be processed any number of times, recycle everything. And then once you decided, yes, I want to make it as a thermoset, we can make a thermoset out of this. Earlier days, PPS, people used to do that. And today, there are many plastics which are allowable, which is possible to do this thermosetting conversion or cross-linking conversion. The most popular one, I'm sure all of you are aware, is XLPE, cross-linked polyethylene. Polyethylene was used as a cable jacketing and tubes, but the challenges of temperature was the biggest constraint. Then people came with peroxide cross-linking in the polyethylene. And today, this itself is a very large segment where you want to sterilize polyethylene, or you want to reduce the moisture pickup, or you want to handle a piping system which has to withstand higher temperature water flowing through this, then naturally XLPE has come into order. And primarily it is chemical reaction and popular in the extrusion application because it can be handled in extrusion without any subsequent thing. Of course, polyester like PET and PVT also processings are possible. And there are few systems established, commercially available products are available, but they are not become very popular because of its own constraints in processing once this cross-linking has to happen. So polyamide, the one we are going to discuss today, is all of you know that it's very good in aberration, with internal properties, and good in flame retardancy, and it can be made into thin walls, etc. So converting this into a thermoset-like material, like Crosslinking material, it became very popular. Polycarbonate, where you want to have transparency and still the temperature has to go up a little bit. I think cross-linked polycarbonates are also available. Okay, the most popular methods by which this cross-linking can happen is thermal. That is by increasing at the time of higher temperature, the molecule reacts and form a cross-link. But unfortunately, the problem is this molecule will start reacting at a particular temperature. So the process width is very small. And within that time, you have to process the material. If you are little premature, then probably the gel formation will be more. And getting the required part will be very difficult. Chemical, you can add a chemical or you can create a site in the molecules which can react, and by changing the pH, by having in the presence of some chemicals, these cross-linkings are also possible. These were all tried earlier, but due to environmental reasons and many other reasons, these are not very popular even now. So then the radiation came, and this can be done with or without a crosslinker. The crosslinker can be inside the compound, or it can react in the molecule itself, and you can form a crosslink. There are specific energy under which these molecules will open up and form the crosslink, and absolutely no influence on crossing. This is a complete like a laser marking, like pad printing, you name it. I think like painting, it's a secondary process. Okay, you complete the process and then you can do a cross-linking process as a separate. Of course, as I said, chemical, there are free radicals. Normally, it is based on free radicals in case of XLPE. And curing take place through carbon-carbon halogen bond, what do you call that, double bond system. And silane is also used in presence of moisture, it will form. Radiation, I think we have got a speaker to, specialist speaker to talk. So there are a lot of lasers, irradiations are possible, like alpha particle, beta particle, high energy electron beam, photon, neutron, you name it. I think whichever can create energy is possible. Even smaller ones like microwave, infrared, X-rays, gamma radiations are also possible to create this reaction of crosslinking. There are many applications for which this crosslinking is started going. Maybe the common thumb rule is you want a thin part, and at the same time, the part should not melt in the application. In the application, there can be a sudden spike of temperature. Then this material, you don't design it for that, in the sense that no material can be designed for a very small spike, but that spike can spoil the part. Okay, and the thin part should be there. And if it is thin, thermosets are very difficult because they may not have the same ductility or impact of thermoplastic. Moving parts, for example, in contactors, the bridges, normally very popular in low voltage application. Lead-free soldering. Today, lead with the ROHS restriction, people are giving up. They want to go to lead-free soldering. And when you go to lead-free soldering, the temperature goes up. When the temperature goes up, the pin don't stay on the part. I think all the parts which have been shown here or soldering is very important, and where you have to go for the base part to be cross-linked. And arc shield in circuit breakers, where there are a lot of arcs are happening. Maybe you want a thermoset-like material to replace ceramics. People try this. They're endless. I think you want a thermoset with a snap fit. Then probably that the chances of using thermoplastic by cross-linking is only there. The RTA of the product goes up after cross-linking. The peak temperature capability also goes up. And XLPE, we all know that for cable, it's very popular. And high current, high voltage application cables. Foams also are very popular. There is no, why I'm showing this application is there is no restriction of only injection molding or anything. It is possible to do anything. Maybe a foam can also be cross-linked. And in polyamide, you will see that with the gamma radiation, E-beam, chemical cross-linking, you can enhance and cross-link the polyamide so that it can start performing better at higher temperature. And in FPL, we have FOMPOLY X, which is a cross-linked series. And we have few grades in nylon 6 and nylon 6X, with glass, without glass, with flame retardant, without flame retardants are available. And some of the, maybe you can go to our website, you should be able to see these products. And of course, we also produce STARFLAM Crosslink here with a licensing from Ascent. And there are a few customers who started using this product in Asia in a big way now. And FPL has won some innovation award for this cross-linked polyamide innovation. And we also have patents on this product for the Asia. And cross-linked polyamide from Poly X, it can be cross-linked using electron beam radiation, as well as by Gopal 60 gamma radiation process. What you get out of the product is a significant improvement in RTI and multifold increase in hot wire ignition temperature, improved wear resistance, and improved chemical resistance. The metal doesn't react that quickly, even in strong chemicals. And hot pin penetration performance improves. You can maintain most of the basic characteristics like flame retardancy. Characteristic of flame retardancy reduces the creep and under load because of the crosslink. High temperature performance above TG is possible, and improved dimension stability under load. Okay, so these are all some of the advantages. Anyway, now I have speaker Alexei and Miguel who will be talking more about it. Back to Alexei and Reshmi. Thank you.
Okay, I will take over. I'm sharing the file. So, can you see my screen now?
Yes, we can see the screen.
Okay, perfect. So today is a kind of practical webinar. So I will try to share a bit of what we know, of what our customers are doing, and how to work with it, let's say, on a very practical. We will not go into detail of chemistry, but let's say what can it bring and what we can do. So
just a minute,
yes.
Can you put it on slideshow? I think then it'll be much better
yes.
and more easily visible to everyone.
Yes.
Yeah, great.
Okay.
Yeah, yes.
Okay. So when customers are asking, hey, what can we do? What is it? Say, high heat short term, extreme temperature for a short period of time, or a material that has to withstand condition, but we are not forecasted in the beginning. Let's say it's best material under failure, under extreme conditions. So what it brings practically? High heat short term. So we will see in the next page what it means. Insolubility. In some cases, it's important, and especially you have to know that if you are trying to measure the solution viscosity in formic acid or sulfuric acid, you simply cannot do it because it's insoluble, and it's the way you are measuring the J rate, say the crosslinking percentage. Infusibility is a real advantage in electrical application, and in some cases you have improvement in dimensional stability, and especially in high temperature service condition. It really improves the creep resistance and the integrity of the part. And it keeps the integrity of the part around the melting point, meaning that it's a single material we have that can work so closely to its melting point. And creep resistance at elevated temperature finds more and more application, and especially in automotive now. So how it works? On the principle is quite simple. Customer is receiving from us a ready-to-use compound. When I say ready-to-use, this can be grade, as Mr. Shikar said, that can be flame retardant, that can be glass reinforced, that can be colored, In some cases, it can even be laser markable. So it's really a one pack, one granule in use. Then the customer is molding the part. He's molding the part on a normal molding machine with nothing, no special layout, no special precaution to mold the part. And it's even possible at this stage to regrind the part, meaning that you are not making any losses in process on this material. And then once the parts are molded, there is a post-operation, and it has to be sent to an external company. Like Miguel will present today, there are companies in the world specialized in treating those materials, not only those materials, but are very well adapted to treat plastic parts. And as you will see, it's a growing business for them, meaning that applications are more and more common in the field. Let's say the unicity of our offer is that our material are, let's say, one pack, as explained, meaning ready to use, meaning no variation, and they are very well covered by UL certificates. So UL certificates, for those who are not so familiar, is a kind of warranty given by an outside company, independent, but certifies the performance of the material for flammability, for electrical property, and for mechanical property. And the good thing is that they're warranting this material before and after irradiation, and this gives the possibility to optimize, let's say, performance and optimize the cost. So what is irradiation? What is ionization? I will not go too much into details, but basically you are bombarding your part with a very high energy. And this high energy interferes to the polymer chains. This takes place at room temperature, so it's not a very harmful treatment for the product. And what happens is that, of course, this energy breaks the chain. And there is a competition between breaking the chain and creating a network. And the know-how of Ascend and FPL is to find also the suitable additive in a suitable amount to create this network. Meaning that once the chains are broken by the irradiation, a molecule which is polyfunctional is reacting to the entities that are created to create this network. And this is all about crosslinking. So once more, to make things simple, crosslinking is really applied on molded part. It can be even applied on assembled part, meaning that if you have a box and a cover, it can be assembled. It can be made directly on packaging. So subcontractors doing the irradiation do not have even to open the card box. They do not have to manipulate. They are just manipulate card box. So it's a matter of sending them, irradiating them, and sending them back. It can be done in presence of metal and inserts. Then I think we will talk more about it maybe if needed, but there is some limitation because, of course, if there are too much metal, there can be some shielding of the rays. So precaution has to be taken in terms of packaging, but it's still possible. And people in connectors world are doing that already industrially. So once more, supply granules in granules forms, so nothing to be treated, injection normal way, and treatment normal way, and send back to customer. So practically, how we can test that? How can we be sure that the material did react? Because basically you are not changing the shape, you are not changing the weight, you are not changing sometimes the core, you are just sending some part outside and receiving them back. So for this one, a very simple test is what we call the hot pin test. So basically you saw this pin, which is applied to a specimen under a load at a certain temperature. So to make that thing short, 350 degrees C, 1 kilo, 1 millimeters, and you apply to the part. What happens? If we see what happens on these pictures, on the left side, you have a plate that has been tested, 350 degrees C, 1 kilo, and then what you see, of course, you are more than 90 degrees C above the melting point. So what happens, as you know, in plastics, once melting point is over, then material melts down. And you see here the print of the pin. It goes through the part. And if you look at the pin, the material is stuck to the pin. There is a hole formation. And you see the same plate after cross-linking, you see that you just have a small print of a specimen, meaning that material could withstand 1 kilo at 350 degrees C for a certain period of time without melting. So this is why we say we are converting thermoplastics in a thermoset, because material is not melting anymore and it's not sticking anymore. And sticking is so much important for people in electrical application. Because when you test, for example, a contactor, most of the time the contactor fails because at a certain period of time, the contact gets so hot, but it sticks to the plastics. And then end of the story. With this material, you have no sticking, you have no deformation, so your material can last much, much longer. So this is a picture of a very practical application. So this is a small application. So say, why do you present this small part? It's a small part, but it's a very important part for us because it's for a supplier, a manufacturer, or a device that everybody has in the house. So it's really appliance, and hundreds and thousands of these parts are made in the world, everywhere, not only in Europe, but also in China and everywhere in the world. So this is a kind of a part in a, I cannot disclose too much, but let's say an iron, let's say, and this part was in thermoset, and they could replace this part due to this high heat short-term capability. And then you see the part, after a test at 350 degrees C, you can see that here also you can only see a small mark on this part. So this is an industrial part on stream, and maybe you will see this small part in Miguel's presentation in a bag. So just to see that it's not it's really high volumes, and it's important because today customer still has an impression that it's an exotic application process. It's no more an exotic process, and everybody is using it not only in appliance but also in automotive now. So what it can bring practically to the product? Here you see a normal nylon 6/6 flame retardant. So we place in an oven a specimen that you can see here. So when you place the specimen in an oven at 295 degrees C, it's still cold, you see nothing. After 1 minute, materials start to deform. And then after 2 minutes, once heat take up the plastics, it really melts away. Here you only have some drops of plastic somewhere. If you take the same material cross-linkable, what do you see? If the material is cross-linkable but not cross-linked, you see that it already reacts, meaning that after 20 minutes, material gets deformed, but it's no more in liquid form, meaning that already with the additive we place in, there is a reaction to heat. But if you cross-link the material at 100 kilo gray, what you see, even after 2 hours, the material gets distorted but maintain its shape. And this finds a lot of application, and it's really a clue that the material can withstand high heat for some time. Of course, we have other products which are more designed for E&E application. This one is a Polymer 6/6 with glass fiber, flame retardant V0 with yellow carb and glass fiber. And you can see that you can finely tune the resistance of the material with the doses applied to that. And you will learn in the next presentation, but of course the cost is linked to the doses applied. So you can finely tune the doses to your application just to fit the minimum of your needs to optimize cost. So the real question of customer is, yes, it withstands high heat short term, but what is high heat short term? What heat? What duration of time? So we made our own approaches on which we can change the weight and we can change the time. So we basically draw some curves, let's say. On this picture, you can see for example, this product irradiated only 25 kilogray, which is not a lot for our product. And you see here time ranging from 5 seconds to 1 minute and weight from 4 megapascal to 32 megapascal. And if you see this part irradiated now 55 kilogray, which is much more, you see the print of a pin, it's much low, meaning that for for example, 7 megapascal, we can say that it can survive almost 1 minute. Of course, if we would need to survive a higher weight for a higher period of time, you will have to increase the doses applied. Then I would say, is there any change on your plastics? Yes, there are. Because when you do the irradiation, you see, for example, there is a slight elevation in temperature on your material, and sometimes it can change the structure of a material. So we have the knowledge to make colors, very nice and fancy colors, but remains stable after irradiation. So you see the red dot is a clue that material has been irradiated 100 kilo gray. So we can design stable greens, you can stable yellow, stable purples. But in some cases, we have capability to design product that changes color after irradiation. And it's mandatory, for example, for safety part in automotive, because the part has the same reference, has the same weight, has the same characteristics, but they want to make sure that the part fit on the cars will survive and has been treated, because it's a safety car for braking systems, for example. So in case of, be aware that we can add to the product a testimony that the material change. This is a slide I added recently just to show you that we are collaborating with French university for aircraft. They are realizing that now aircraft are no more in metal, let's say in aluminum, but they are more and more in plastics, and they have to shield some piece against the high heat. And here you see, for example, a flame retardant polyamide 66V0. But here we're not testing about a small fire. We are testing about a flame of 116 kilowatt per square meter, a flame temperature of more than 1000 degrees C and a duration of 5 minutes. So even a polyamide, which is flame retardant, resistant to fire, after the testing really vanish. You are nothing left. If you find same material Crosslink, then you see on the back plate, you keep some kind of char and integrity. So we have a lot of customers now in many fields that are thinking of using cross-linkable plastic for shielding against fire. We are not more talking about high resistance, but extreme resistance. Okay, so I'm already late, so I have to go fast as usual. So from this, we built a range. So in our range, we have pure polyamides, but are not flame retardant, just cross-linkable. We have a product that are glass reinforced. We have here products that are flame retardant and V0, typically for connectors. And we have some exotic material. I will pass them very rapidly just after that. So to make a long story short, R1002K, pure 6.6, just cross-linkable. Interesting if you have designed a part, for example, that needs to be quite soft. You are making some snap fit. You are making, you need a bit of flexibility, but under failure, it's too hot and the material melts. This might be the solution, especially in the automotive industry. Then if material needs to be a more stiff, need to withstand more heat, more HGT, we have this polyamide 6 with 30% glass, which is cross-linkable, which find use in automotive application. But not only in the automotive. You know, there are some connectors that are not flame retardant, they're only there to pass a kind of signal, but can fail under high heat. And then you can use this product too, of course. It's important to say that it's one of the very few materials that can survive lead-free soldering, and on this, on the one we can use snap fit and hinge, let's say. Most of the time you have to use or very expensive material or thermoset, but designing a material that can survive hinge with lead-free soldering are not so common. And we have this one, it's very well covered by UL card, and it's in use by big EOM during connectors. Then we have this one, which is more, let's say, a specialty. It's been designed mainly for arc chambers, and we take into advantage this high heat resistance, and we even design a product that create a kind of shield against the arc. So when the arc is bumping into the arc chamber side, you create a kind of ceramics that prevents the arc from flashing away and to melting the plastics. We have also flame retardant grade. So this one is already in use in India for application in E&E. So this is a kind of specific grade. His interest is mainly in low warpage and very safe product in terms of burning. It releases no toxic fumes. It's very stable material. And we have this one, which is also very famous. It's a nylon 66 with 30% glass, V0 halogen free, which is cross-linkable, and that finds application in E&E and also in trains, because it passes the more stringent requirements for trains, meaning that the material can be applied also for sleeping trains and for train that has to go into tunnels. So it's a very, very safe material for that. Okay, so I'm almost done. So I will pass over to Miguel that will discuss about, let's say, the last part. And I insist, this is a very important part, because to succeed on such a project, really, you have, it's a story that you cannot do alone, because you need the knowledge of people doing irradiation, because you will see that even you have a good material, if it's not irradiated correctly, you can spoil your material. So I will just pass over to Miguel.
Okay, thank you, Alexis. I'm going to share the screen. Okay, I hope that everybody can see the screen now. Is it?
Yes, we can see the screen.
Thank you. Thank you very much.
Can you take it on slideshow?
It's already in a slideshow, no? Or, let me see.
Okay. Okay, I mean, it's visible to me. I'm okay with this.
Okay, I hope it's okay like that. Okay, thank you very much. As said before, my name is Miguel Morales. I'm Sales and Marketing Director of IONISOS. IONISOS is an industrial service provider that is focused on in the radiation business, mainly in the markets of medical devices sterilization and cross-linking of plastics and pipes and tubes. So I would like to give you an introduction about radiation processing. It covers the type of facilities and the basic interactions between irradiation and matter. And after that, I will give you also some information about the applications and, what is more important, the process conditions that we have to take into account to define the irradiation process of the plastics. I will finalize with some introduction about IONISOS, the sites that we have in Europe, and some information about the company. So, okay, let's start. Okay. So the three types of facilities that we can have to irradiate products are gamma rays facilities, electron beam, or X-rays. The first one, gamma rays, is the source that we use to irradiate the products is cobalt-60, which is an isotope that emits gamma rays when it decays. These cobalt-60 facilities are, let's say, one of the possibilities we have, but not the one that is more used. The one that is more used for this cross-linking of products is the electron beam facilities. In this case, we have an accelerator, particle accelerator, that will generate a high energy beam with which we will be able to ionize the materials that we want to treat. The third type of facilities, or the third type of technology that can be used, is X-rays. This is a new technology that has been started to use with medical devices that hopefully in the future will be also used for cross-linking. In this case, we use a high energy beam to convert it in X-rays. To do this, we need a target, a high dense metal target that will generate the X-rays when the electrons decrease their speed. This is called Bestralum. We are dealing with ionizing radiations. This means that the radiation that we are going to generate, needs to have certain energy. We are going to have energies between 1 mega electron volt and 10 mega electron volts, depending on the source and the type of radiation. This energy will be able to ionize the products. If we look at the characteristics of these three types of radiation technologies, E-beam, gamma, and X-rays, we can see that the main difference between these type of radiations are related with the penetration capacity of the radiation and the dose rate that we can deliver. If we talk about the penetration capacity, we can say that the electrons are the ones with less penetration capacity. This is because electrons have mass, and this reduces the energy of the electrons when interacting with matter. While in the case of gamma rays and X-rays, we are dealing with photons, and in this case, the penetration is much higher. Let's say that is infinite, due to the absence of matter in the photons. In the other characteristic that we have to take into account is the dose rate. In the case of the electrons, the dose rate, the time that we need to deliver the dose to the product is really short, basically seconds. This has some advantages in terms of productivity and turnaround, and also in terms of limiting the oxidation that we can have on the product. Because
just a minute, Miguel, can you stop the translation which is coming at the bottom so that the screen is a little bit bigger? There is a translation which is coming at the bottom, and I'm getting a request from the audience. So if you can just remove that translation, I think the screen will be a little bit bigger.
Okay, so let's see.
Yeah. Now we've gone to screen sorter. You'll have to go to slideshow.
Okay. I'm going to start again. Let's see.
Yeah, now it's very clear.
Okay, good. Okay, thank you. So, but I don't know if the translation is still there or not.
No, it's still there, but like the screen is bigger.
Okay, good. So let's continue like this. Okay, let's see if I can move. So the next slide. The next slide, we have the layout of the different facilities. In this case, we can say that all facilities has the same layout. We have a concrete cell in which we have to, in which we are going to place the radiation source, the electron of the cobalt, and the treatment area. This concrete cell, it will act as a shielding. Let's say we are going to keep all the radiation inside, and so the people that is around the facility can access it freely. The second part of the facility is the conveyor system or the transport system that has to transport the product to the treatment area. In this case, we can have like conveyor, tray conveyor, pallet, overhead conveyor, depending on the type of facility, or a continuous product treatment system, which is that is used for the treatment of cables and pipes. In this case, we have a drum, unwind the cable, pass it under the beam, and then wind it back after the treatment. Now, if we look into the interaction between the radiation and the materials and the plastic that we want to treat, we first of all need to say that the energy of the irradiation that we are dealing with is only enough to interact with the electrons of the atoms and molecules. If we limit, as this energy is limited, we cannot interact with the nucleus of the materials. This is important to understand that there is no induced radiation during the process. Once we have this clear, we just, as previously said, we are going to be able to ionize the atoms, and through this ionization, we'll generate free radicals that will help us to will react with the other free radicals in the product, and we can have polymerization, curing, crosslinking, or grafting, depending on the type of polymer. The main applications are related with crosslinking in any case. Also, it's important to say that there is no need to use chemical photosynthesizers. The radiation will be the initiator of the reaction. This technology is compatible with a wide range of molecules. And these are permanent changes. Once we have modified the structure of the polymer, these changes are stable, so the properties will remain. Okay, now let's talk about the applications that we can have with these technologies. Just a little bit of history about this technology. Let's focus on crosslinking, as I said before, because it's the main application. The doses that we are going to use are between 100 kilograms and 200 kilograms, depending on the plastic and the application and the results that we want to obtain. We mainly are looking to improve chemical and thermal properties in the product, though also we can improve the mechanical properties of the product. And to give you some history behind, this technology was developed in the 70s and to treat cables and pipes. As at that time, the treatment of pipes, polyethylene pipes by irradiation was an alternative to other existing methods to crosslink pipes as peroxides and sealants, as we have seen before. The technology and the applications expanded in the 90s to parts, to individual parts. This came also through the new e-beam sites with conveyors, with tray conveyors that were able to treat boxes and individual parts. And the last application, just to give you some examples, is related with textile fibers. In this case, we treat polyolefin-based fibers to improve their chemical and thermal properties. Also, it's important to understand that some of the polymers that are compatible with this technology will cross-link, let's say, naturally without the addition of any additive. Those polymers are, for example, the polyethylene, while other polymers, polyamide, the ones that we're talking about today, or polypropylene, will need an additive, an agent, to be able to cross-link. So this is an important point to understand also. The properties that we are looking to improve, the first one that we have identified here is the chemical resistance improvement. In this case, we can see that by cross-linking the product, we are going to be able to increase the resistance to chemicals of polyethylene and other plastics. This property is applicable to packaging materials, for example, if we want to contain solvents or gasoline or oils. It will help us to have a packaging material made of polyethylene or polypropylene, for example. The other important property that we are looking into is the thermal resistance. In this case, we have an example of a polyamide that we have irradiated by E-beam and by gamma to the same dose, and you can see there how the plastic parts that were not cross-linked are not dimensionally stable to temperature, while when we irradiate the parts, we just make a big difference, and the part is quite stable at high temperatures. Here we have another two examples, more related with the treatment of pipes for underheat floor. This is, let's say, one of the most common applications at the moment. And these pipes made of polyethylene, after the treatment, can withstand a peak temperature of 85 85 degrees, while normally they can only go up to 65 degrees. And also for the service temperature, we can be able to use these pipes for heat applications, while normally this polyethylene would not withstand the high temperatures of the water. And the other application is related with the electrical parts, as you can see there. In this case, by cross-linking the polyamide part, we can improve the peak temperature that the product can resist, quite considerable, as you can see there, to up to 450 degrees. This helps us to withstand arcing and high temperature of the contacts. And if we look into the process itself, we have to take into account first the dose that we need to deliver to the product. And to achieve that dose, we will need to deal with several irradiation parameters. The first one is the energy of the electrons. Let's focus on E-beam because it's the more used technology. Okay, so the first irradiation parameter that we need to focus to see is the energy of the beam, of the electrons. This energy will determine the penetration capacity and also the dose that we can deliver to the product. The second parameter is the speed that at which we are going to expose the product. This speed can go, for example, from meters per minute when we are treating parcels and boxes in a tray conveyor, to hundreds of meters per minute when we are treating in continuous mode cables or pipes. The other parameters that are important is the scan width. We need to adapt the scan width of the beam to the width of the product, the width of the tray, or the number of passes of the cable under the beam. Here we have an example that we can look with more detail. Here we are cross-linking some individual parts made of polyamide. And in this case, we receive the products in boxes of those dimensions, 30 by 20 by 20, with a weight of 4.5 kilograms each. Okay? So in this case, the target dose can be 100 kilograms. As you can see there in the diagram, we have placed the boxes. We place the boxes that we are going to treat on a irradiation tray. We are using E-beam, as indicated before. This, as we said also before, the E-beam will deliver a high dose rate, so that will make the treatment quite quick. This means that the product will be under the beam for several seconds. And also we are treating with electrons. These electrons have a limited capacity, penetration capacity, so we will need to treat the product on two sides. This means that we will have to turn the product 180 degrees to be treated on two of their sides to have a complementary dose profile, as you can see there in the graph. The dose will be a combination of those two passes. As a thumb rule, we need the maximum surface density that we can treat is around 7.5 grams per square centimeter, due to the limited penetration capacity of the electrons. Also, because of this, the type of profile the electrons the way the electrons will deliver the dose in depth, we will have some uniformity in the dose inside the product. This means that if we are targeting a minimum dose of 100 kilograms, because it's the dose that we need to achieve the desired gel percentage content, we will have other parts in the box that will reach a higher dose, in this case 163 kilograms. This means that we will need to check that maximum dose is also acceptable for the product, and that the properties of the products are enough homogeneous. It's an important point in the process. Just to give you some important aspects to consider while defining the process. It's important that to know that E-beam is more compatible with the small parts due to their limited penetration capacity. We can also treat bigger parts, but we need to make sure that the process is going to be homogeneous. This means that the dose is going to be enough homogeneous for all the parts when these parts are big, and also that the penetration capacity of the electrons are able to treat the inner parts of the part. Also, it's important to define the size of the boxes in which we are going to put these parts. As said before, the maximum penetration capacity of the electrons is 7.5 grams per square centimeter. So our advice would be to try to fill in the box all you can and make the box as high as possible to reach that surface density, and don't leave empty spaces on the box if possible. Also, it's important to understand that the dose that will be delivered to the product will increase a little bit the temperature of the parts. And we can say that normally it's around, it will depend on the heat capacity, but what our experience tells us that we will increase around 0.5 degrees for each kilograde that we deliver. So this means that normally we will deliver the dose, which is normally around 100 kilograms, in several passes. We don't want to deliver all the dose in one pass because the increment in the temperature will be too high. So normally we are looking at around 4-6 passes treatment. Some of our clients also reduces the boxes. Our advice is not to reuse them more than 2 or 3 times, because the carton will get brittle and then we will have problems with the levers and so on. Boxes broken and so on. Okay, so if we look into the economic part, just to give you some ideas on how to improve this part, we would advise also to design the boxes to fill in the irradiation trays or the taught gamma conveyors completely. Just to give you an idea is the irradiation trays are normally 100 centimeters by 120. So make your boxes multiples of this surface so we can fill in the tray as much as possible. And the same for the irradiation containers in case of gamma. Try to use also the full penetration of the electrons. So try to reach that maximum surface density of 7.5 grams per square centimeter. And also, as Alexis said before, try to select the dose that is needed. Don't overdose the product. If the product, you know that the product will reach the right specification with 75 kilograms, let's target that dose. Don't go more than that. Okay, and just to finalize this part, every time that we want to put in place one project, Crosslinking project, first of all, as we have seen before, we need to identify the materials and the additive that we need to use, and that will match the specification that we are looking into. There is also the need to do an economical flexibility study in comparisons with other materials, taking into account and considering all the process, molding, logistics, I mean, all those irradiation, all that is involved in the process. And once all that is clear, then we will need to define some trials. And these trials will give us the final answer about if the process is possible, and will give us also the right dose that we will need to use to treat the product. What we normally do is we treat several samples to different doses, for example, 50, 75, 100, 125 kilograms. And with those samples, we plot some curves about the changes in the properties and the gel content to identify write those that is needed for the process. Okay, so this is for the irradiation applications, and now just a short overview about IONISOS. As said before, IONISOS is an industrial sterilization and crosslinking service provider with facilities in Europe. We have these two businesses, sterilization and crosslinking, and we use 3 technologies to do so. The 2 first technologies that we use and that are compatible with crosslinking are gamma plants and electron beam. There is a third technology, which is ethylene oxide, which is a gas that is only usable for the sterilization of medical devices. These are the facilities we have in Europe. If we look into the e-beam facilities that we have an e-beam plant in Spain, close to Madrid, in a town called Tarancon. It's a 10 MeV plant in which we cross-link parts in boxes and fibers in this case. And we have another e-beam plant in Chaumigny in France. In this case, the same than in Tarancon. We are able to cross-link individual parts that are delivered to us in boxes with a 10 megaelectron volt machine. And the third e-beam plant that we have is the one in Bautzen, Germany. In this case, we have an underbeam system that is designed for the treatment of pipes and cables. All we treat there. Just to give you an idea, we have installed a new 30 beam in Bautzen some months ago due to the high demand in this sector, which is also we are receiving requests from this for cross-linking parts in our plants of Chaumigny and Tarancon quite oftenly, and it's a growing activity for us. Just to give you an idea of how important it is, this business, the cross-linking business is for us, it's around 20% of our sales in all Europe. And here you have some of the products that we normally treat: fibers, pipes, cables, and so on. The other 80% is dedicated to medical devices sterilization. And just to finalize, just to tell you that in IONISOS we have a sustainability strategy in place that we let's say deploy around 4 axes. We have include sustainability in our governance and communication. We are always looking to provide the best working place to our employees. We try to include sustainability in all the service agreements that we have with suppliers and clients as a key factor, and also we measure our carbon footprint, put in place actions to reduce it, and just to contribute to local activities and associations. Okay, so this is it. This is all from my side. Thank you very much.
Yeah, thank you. I think very good session, very good presentations we've had. Mr. Shekhar discussed on the comparison of thermoplastics versus thermoset, giving us an introduction regarding what exactly is cross-linking, what are the technological innovations Formulated Polymers is doing in India, what are the advantages in terms of enhanced production for a thermoset material, and for thermoplastic, a very high thermal performance. So I think it's building up bridges and having a material which performs far superior than if you take it individually as a thermoplastic or thermoset. I think he's discussed around the key methods of thermal and chemical radiations, the various applications, the cross-linking methodology in terms of gamma, electron beam, chemical cross-linking. Whereas for the formulated polymer product range, we are using gamma radiations, basically the cobalt 60 gamma radiation. So thank you very much, Mr. Shekhar. I think the next session was with Alexei. He covered up the advantages of cross-linkable materials, the UL cards which are present with the Ascent Performance materials, thermal properties and checking how do we test these thermal properties. So he discussed in detail regarding the hot pin test. Then in terms of stability, there is heat stability, thermal stability, creep resistance, dimensional improvements after cross-linking. He also discussed on the chemical resistance in terms of like even formic acid or sulfuric acid. After cross-linking, the polyamide is not soluble in even those harsh chemicals. So I think a very good session by Alexei, especially when he discussed it with applications and specific STARFLAM grades, both unfilled grades, where he talked about polyamide 6,6 as well as 30% glass filled. Along with applications, I think one of the best parts was in terms of secondary operations, that even after cross-linking, we are able to perform the secondary operations and soldering, even with the modified technologies, because it was earlier the lead antimony soldering methodology, whereas after the REACH and ROHS compliance requirements, there are the new which require higher temperatures, and even for these higher temperatures, because of the better performance, we are able to perform even the basic soldering operations, laser marking, etc. Color stability is there. So thank you, Alexei. I think to continue, Mr. Miguel Morales, he took up radiation technologies, discussed in details. I think that's where we also had a little bit gap in terms of most of our customers are actually sending the samples abroad, either to US or Europe. So to try to get them back to India for the final assembly. So that's a gap which we see, and I think that's also an opportunity if we look at it. Miguel discussed on the cross-linking applications, principles, when to use, and he's even talking about no initiator required for the radiation process. He discussed on detail regarding the gamma, the ionization, EB methodology, as well as the EO, that is the ethylene oxide methodology, which IONISOS is applying to various applications. I think we were discussing more on the flame retardant, but it was good to have an insight that in packaging and textile applications, also there is a lot of usage for these radiations, especially in case of polyolefin fibers as well as polyamide fibers. Another thing which we understood was in terms of what is the depth, what is the dimensions when we look at that. Good that the organization is growing in Europe. We hope that possibly they might look at Asia, Southeast Asia also in the near future. I would like to take up the question answer session because we are all running short on time. So there's a question from Mr. Bhavin Panchal. He asks, I think this is for Miguel, because he's asking about which type of rolls were you talking about? I mean, with plastics, is it cling film or something else? So I think Miguel, you can take up this question.
Rashmi, if you see, he has answered himself. He said, ignore this question. He's got an answer.
He's got an answer. Okay.
Okay. Doubt clear. Please ignore my last question.
Okay. Okay. So then there is a question whether color change will happen after the irradiation process. So I think that's where they'd like to understand, although Alexei made it very clear that irrespective of the colors. So I think the question would be more related to whether there are certain pigments which have to be used, or across the board, whatever pigments are used, the standard ones, they will be meeting, and there will not be any change after the irradiation process.
Yes, to make things clear, for colors, we can make what we want. Maybe my picture was not clear enough, but let's say if we want to formulate stable colors, we can do it. But we have the unique opportunity that we can formulate some colors that can be a clue for radiations. And most of the time, the customer do not want the color to change because it's related to design. But in some cases, especially for safety parts, and especially in the car industry, they they want to make sure 100%, but they cannot put on a vehicle, on a car, a part which is not cross-linked, because the part which is not cross-linked will not survive the heat, the creep, and might make the car dangerous. So let's say for colors, it's upon request, of course, but we can make stable color if needed, of course.
Okay, thanks, Alex. I think there is one question asking, can it be recyclable and biodegradable? I presume there's a lot of awareness in terms of recyclability, especially with our sessions where we talk about REACH, ROHS, etc. compliances. So, now since most of the organizations are looking at carbon dioxide reduction, so I think it's like a genuine question regarding the recyclability and the biodegradability. Biodegradable, I don't think it is, but maybe recyclability we can take up.
Before cross-linking, you can recycle any number of times. There is no. It is like any other part. But once cross-linked, I think like Thermoset, it is difficult. But if you still want to use it, maybe you have to spend a lot of energy of grinding it into powder and then mixing it, but it will remain like a filler. So before cross-linking, yes, you have flexibility. After cross-linking, there are no flexibility. It is like how you handle a thermoset, you may have to handle this also.
Exactly.
Then I think, Alexi, this is directly for you. There's someone who's really appreciated your presentation. I think most of us do it every time you make a presentation. He's asked, we'll appreciate a few comments on effect of types of FR, halogenated and non-halogenated FRs in the cross-linkable polyamide technology. This is Mr. Prasad Madamama.
Then I think we are very complementary, let's say both companies, because let's say the STARFLAM range has been designed, let's say more to be based on eco-FR, but in the FORMPOLY range, let's say other types of flame retardant are used. So basically we can cover the range of most of the flame retardant, let's say, with different effects. And let's say, I think this is great because as I explain all the time, there is no perfect product. There is a product that fits an application, but a product that patient can be losing for another one. So it's good that we have a range that covers all the type of flame retardant. And regarding, let's say, the influence of cross-linking on flame retardancy, sometimes it's strange. And in this case, material does not burn anymore.
Near future we can hope for, but I think Miguel can give an update regarding what would be the cost differential in Europe itself.
I mean, the situation of the market in Europe is a little bit biased due to the high demand for medical devices at the moment and pharmaceutical products. So that is altering a little bit the prices from my point of view. I can tell you that the prices here are quite similar to the ones in USA, but I'm not familiarized with the prices in Asia. Sorry.
To answer that partially, I think it all depends on what is the quantity, okay, how big the consignment is, how much you want to radiate, what is the part thickness, okay, and there are many complexity. As Michael was saying, first you have to do a trial of different radiation to find out which is satisfactory answer to you, and then the cost can be worked. So it is an expensive process to costing subsequent to that.
But the point is that at the end of the day, if you compare the thermosets with the thermoplastics irradiated, there should be some advantages. Otherwise, there won't be an alternative, and it's an alternative. So that could be a good reference, I think.
Yeah, okay, thank you. Thank you, Mr. Shekhar, Mr. Miguel. There is one more question. I think this is for Mr. Shekhar. What are the precautions needed to take during the injection molding process? So I think it's initially whether we use the same process or there is a different process or there are certain precautions during the injection molding before irradiation.
Thumb rule, I would say there is nothing to be taken as a precaution. There is nothing specific about it that one has to care. Of course, we have to care that the part should not pick up moisture, because during radiation, we should not be losing the energy in drying the product. So these kind of basic precautions you have to take, but otherwise there is nothing specific about molding. Okay. And molding doesn't have much influence on the crossing part. So I think I answered Mr. Atik Sudik question also. Maybe you can read out for Lexi.
Which one is that now? I've lost. Okay, I'll come to the next question.
No, since this is connected to this question, I think Alexi can answer. I think this question is from Mr. Sipik, who is asking that we are using RF0023K, but sometime after gamma radiation, when we test, it fails in pin penetration.
Is it because of
any molding condition?
Yeah. And dosage also he has given 100 kGy.
It's an impossible question to answer without analyzing the part. Let's say without understanding. Let's say if the formulation is okay, that's what we think. If the formulation has been well irradiated, there is no chance that the product is not cross-linked. So if material fails, it has to be. We have to find the root cause somewhere, where or in the molding, or in the material, or in the irradiation. Like Miguel said, this product is quite heavy. So we need to be sure that in this case that the packaging is okay, because as the density of this material is quite high, just imagine that we go over this, I don't know, it's 7 point something density the density limit, then it can well be that the part on the middle are not effectively receiving the dose that they should receive, because this is a quite heavy material. The density of this material is 1.6 something to my mind. So maybe one should have to look at the packaging itself. Maybe at least there is no reason that the material is not cross-linking if you receive the right amount of energy and if material is formulated correctly and processed correctly. But this is what I said from the beginning. Yeah? To succeed with those parts, it's really something that you cannot do alone. You need to have very good relation and confidence into your irradiation provider, because there is some knowledge in this one, and we think, and there are some limits, there are some requirements in terms of packaging, and sometimes it really makes a difference.
Just to add something else that is important, every time we treat a product, a box, we do, before we start the routine production, we do what we call the dose map in the product. What we do is we place dosimeters in all the volume of the box to make sure, as Alexis said, that the dose reaches all the volume of the box. Okay, so once we have that dose map done, and we have identified that the dose is going to be at least the minimum expected one, then we can start the routine productions. It's an important step in the process, in the design of the process, to verify that the density and the size of the box is compatible with the penetration of the electrons.
Thank you. Thank you very much. I think we have run out of time. If for any additional questions, I think we'll answer them directly through the email process itself. Coming to our session, we have the next webinar, which is planned, which is on applications of FR compounds. I think we'll have a good session, and a lot of participants because it's very interesting where all should we use our compounds, and what are the new applications and the new trends, especially with electric vehicles, etc., coming up. So what are the opportunities which we are looking at? So that would be the next session, and that will be somewhere in September. So I think I would like to thank all of you, thank the entire team for discussing in such detail, giving us a comprehensive overview. We'll come back to you with the next webinar. If you want to communicate with anyone, Alexi or Miguel or Mr. Shekhar, so I think we can coordinate. The email IDs have been shared. For any direct questions, you can coordinate, or we can coordinate for any additional information which you require. The presentation will be available on YouTube. So in case you have missed part of it due to your busy schedules or whatever reason, you're traveling or something, then you can access the presentation on YouTube also. And we definitely would like to answer your questions. So once again, thank you very much. Thank you very much.
Thank you.
For a wonderful presentation.
Bye. Bye, everyone.
Thank you, Mr. Shekhar. Thank you, Mr. Alexi. Thank you, Miguel. Okay, thank you. Bye-bye.
Bye.
Bye.
I think, have you stopped?